at this chart of values. Okay. So when you plugged in negative 100, you have negative 1 over 100, or negative 0.01. Okay. And then when you plug in negative 10, you'd have negative 1 over 10, or negative 0.1. When you plugged in negative 2, you'd have negative 1 over 2, okay, or negative 0.5. Okay. When you plug in negative 1, you'd have negative 1 over 1, which is negative 1. Okay. So on the positive side, the same thing is happening, but with positives. Here you'd have 1 over 10,000. Here you'd have 1 over 1,000. Here you'd have 1 over 100. Here you'd have 1 over 10, 1 over 2, 1 over 1, which is just 1. Okay. So I'm going to plot some of these points. I specifically haven't done 0 on purpose. Okay. I walked around, saw some of the answers. We're going to have a little discussion. All right. So when I plugged in 1, I got 1. So I have the point 1, 1 on my graph. When I plugged in 2, I got 1/2. And when I plugged in 10, should be out here, I got like 0.1, something like that. Now, if you're not sure what's happening, look between 0 and 1. Let's say I had plugged in 1/2. Okay? What would it be if I did 1 over 1/2? Yeah, 2. It's the reciprocal function, right? Like 1 over something is its reciprocal. That's going to actually give me 2. So when I plug in 1/2, I get 2. What's going to happen when I plug in 1/10, a real small x value? I'm going to get 10. Okay, let me get something up here. I know. Sorry, I've got to recalibrate. Okay, so what's happening here? And then what happens when we plug in 0? So when we plug in 0, it literally looks like this. 1 over 0. What is 1 over 0? Undefined. We don't have a value for that. So can I plot a point on the graph? No, I can't go, oh, I plug in 0 and it calculated to be this. I can't put a point there. There is no point there. So can the graph connect from this side to the other side? No, because it can't cross over there with any point that shows up on the graph. So we'll talk about what to do with that later, but they're definitely disconnected, right? So this creates one branch on this side, on the positive x value side of the graph. Now, I drew these arrows. What's really happening here? So right here, this top arrow, is it moving to the left? When I plug in something closer and closer to 0 from the right side, am I getting closer and closer to the y-axis? Yes. Will I ever actually hit the y-axis? No. So it's like this crazy concept in math. Basically, it's this idea. Let's say that I decided I was going to walk to the back of the room, but I was going to do it very like mathematically. And the way that I was going to do it is that I was going to think about each point that cut my distance in half. Okay? So let's say that right now I'm like 20 feet from the back wall. Okay? So where am I going to move to next if I'm going to cut my distances in half? 10 feet. I'm going to move to where I'm 10 feet from the back wall. Okay? So say that I'm 10 feet from the back wall. Then what am I going to do? 5 feet. So I'll move to where I'm like 5 feet from the back wall. Then what am I going to do? 2.5 feet. So I'm going to move to where I'm like 2.5 feet from the back wall. Then what am I going to do? 1.25. Okay? Then what? Yeah, whatever that is, cut in half, right? Okay. All right. So physically, I am a person and I take up space. Therefore, I will run out of room. Okay? But mathematically, will my distance from the wall ever reach the exact value of 0? No. Because when you cut 1.25 in half, you're going to get 0.625 or whatever, right? Then when you cut that in half, you're going to get 0.3125. Then you're going to cut that in half. You're eventually going to get 0.00000, something very, very close to 0. But will you ever hit the definite 0 mark? No. Crazy, right? Okay, so technically your distance would never be 0. All right? So that's what's happening here. We plug stuff in and we're getting so close to hitting the y-axis, but we're not ever actually hitting it. Okay? And then think about what's happening here as we move to the right. Okay? So we plugged in 10 and we got 1/10. We have numbers here to look at. When we plug in 100, we're going to get 1/100th. Is that close to 0? It's close to 0, right? Then we plug in 1,000, we get 1/1000th. Is that close to 0? Plug in 10,000, we get 1/10,000th. Is that close to 0? Yes. Are we getting closer to 0 with each larger number that we plug in? Yes. So as I plug in bigger and bigger x values, the y value is getting closer and closer to being 0. Will it ever technically reach 0? No. So again, this concept, it will get closer to 0 continuously, but will never actually reach 0. Weird? Yes. Okay. But can happen mathematically, right? It's like playing a game with someone. Choose a number between 1 and 2. How many numbers are there between 1 and 2? Infinitely many. Okay, the joy of the world of mathematics, right? Okay, so not this finite set of things. So when we look at the negative values, okay, if I had plugged in -1/2, I would have gotten -2. I plugged in -1 and I got -1. I plugged in -2 and I got -1/2. I plugged in -10 and I got -1/10. Okay, and then I could plug in -100 and get -1/100. So again, I'm getting the same type of shape. And the same kind of idea is happening. Again, here I'm getting closer and closer and closer to 0, but they're negative values that are getting closer and closer to 0. Do they ever technically reach 0? No. Okay? And as I plug in smaller and smaller numbers, I'm getting closer and closer to the y-axis, or numbers that are closer to 0. I'm getting closer to the y-axis, but I'm never actually crossing the y-axis. And these guys cannot meet. There can't be a line that connects them, nothing, because nothing can cross this y-axis, because if you plug in a 0 value of x, you have an undefined value. Is this okay with everybody? So that's what the reciprocal function looks like. All right, so some questions about it. So what happened when x was equal to 0? Yeah, it's undefined. And then, basically because we can't divide by 0. Our mathematics does not have a value when things are divided by 0. Does the graph have a y-intercept? No. Okay, so somebody explain to me why. Why doesn't this graph have a y-intercept? Good. Because how do you find a y-intercept? A y-intercept occurs when the x value is 0. And you just said we cannot find a value when the x value is 0. Okay? So no. And that's because the value is undefined when x is equal to 0. Does the graph have an x-intercept? So look at your graph. Does it have an x-intercept? No. Okay. So why not? Why didn't we get an x-intercept? Why did our graph not cross the x-axis? Good. Okay, so one way is, when y is equal to 0, the equation is not solvable, right? The reason it's not solvable, think about it. If you had 0 equals 1 over x, is there anything that you can change x to get this right side to equal 0? No, there's nothing you can put right here. We'd need a 0 up here to get 0, right? And that's not a thing we can change. The x is down here. Okay? All right, so then there's a little piece of information for you. So we're going to talk a lot about asymptotes in this unit. Okay, I know it's a fun word. Okay, how many of you guys have heard the word asymptotes before? All right, a couple of us. All right, so asymptotes are basically those places where the graph is kind of following along it. but may or may not cross it depending. So here, your note guide talks about vertical asymptotes. Here's what a vertical asymptote would be used as shown. So on the graph, you put a dashed vertical line. That tells somebody you have a vertical asymptote. Okay? And it represents where the graph is undefined. So we're going to go put our vertical asymptote on our graph because it has one. Because was there an x value that made this function undefined? Yes. Okay, so we want to show that on the graph. So we're going to go ahead and put in a dashed vertical line where x would equal 0. And what that is telling the person looking at the graph is that you cannot plug in 0 for x. So we're going to have functions later that are more complicated, and there's more stuff that you can't plug in for x, but whatever it is that can't be plugged in for x because it would make it undefined is shown by this vertical asymptote. Okay? All right, so what I want you guys to do in your group, you have a parent function now, right? We made the parent function. You have the graph on your paper, correct? Everybody has the 1 over x. So here is a new function. It's part of that family. See the 1 over x? But with a couple of transformations, okay? A -2 right here and a +1 right here. Somebody raise your hand and tell me, what is this -2, considering it's affecting the x? What kind of transformation is that? I didn't hear clearly. Some people. Okay, so it's going to be horizontal because it's affecting the x. Okay, is it a translation, a reflection, or a stretch or compression? A translation. Okay, so it's a horizontal translation. Which direction? Left or right? Right, because of the x minus h thing, right? All the horizontal stuff is kind of weird. Right. 2 units. Okay. What about the +1 that's at the end after the reciprocal part is done? What kind of transformation do we think that is? Ashley? Good. So that's going to be our vertical translation, and it's going to go up 1 unit. Okay, so I want you guys then to take your parent function, what you have on that graph, do these transformations to it. So think about what it would look like when you move it to the right 2 and up 1 and sketch your new graph on here. Okay. And then answer these questions. At what x value will this function be undefined? Draw and label the vertical asymptote. And is there a y value that the graph gets closer and closer to at the ends of the graph? Or in other words, what is the end behavior of the graph? All right, so your graph should look like this if everything's shifted to the right 2 and up 1. So you should have something similar to this. And we should have an understanding, now that we know how this graph works, these look straight, because I, as a human being, can't draw you the difference between 1/100th and 1/1000th and all these kinds of things, okay? So they look straight, but we know they're not horizontal. We know they're getting closer and closer to something and approaching that value. So in this graph, at what x value will the function be undefined? X equals 2, because that's what's going to create the 0 in the denominator here. Okay. So then it said to go and label our vertical asymptote on the graph. So to draw and label, a small note. Label does not mean, maybe like in science, like label the mitochondria means point to it and write like mitochondria. So in math, it doesn't mean point to it and write vertical asymptote. It means put the equation, or for a point, the coordinates, okay? So when they say draw and label it, I'm supposed to put it into the graph. Here it is. And my label is this, not a little arrow that says vertical asymptote or something like that, okay? Just to clarify. Some of us know that and some of us don't. Is there a y value that the graph gets closer and closer to at the ends, or what is the end behavior? So a small reminder about notation for the end behavior. And even though it's for this bottom question, I'm just going to write it right here because it's a little bit easier to see. For end behavior, we said we do the limit as x goes to -infinity of f of x, and write what that equals to, and the limit as x goes to positive infinity of f of x, and we write what that's equal to. So the only difference in the notation here, x is going to negative infinity, which means when you go to the far left of the graph, what's happening to it? What is it approaching and kind of staying at? So in the last unit, we were studying all polynomial functions, and at the ends, they were always shooting upward or downward. So we always got an answer of infinity or negative infinity because they weren't stopping at a certain place. They were heading there. As I go to the far left of this graph, does this go towards infinity or negative infinity? The x values go towards negative infinity, but I'm talking the function here, the y values. If it's going towards infinity, it's shooting way up. Is it doing that? No. If it's going towards negative infinity, it's shooting way down. Is it doing that? No. What y value is it getting closer and closer and closer and closer to and basically becoming? 1 in this case. Okay? So in the last unit, you guys were always like, it's either infinity or negative infinity. So in the world of math, is it always negative infinity or infinity? No. In that unit, was there a reason that it was always like that? Yeah, all our functions were shooting up or down. We didn't have anything that behaved like this. Okay? All right. As x gets bigger and bigger and bigger towards infinity out here, what happens to the y values? Are they shooting up towards infinity? No. Are they shooting down towards negative infinity? No. Are they approaching and getting closer to one specific value? Yes. They're kind of leveling out at one value. And what is that one y value? 1 again. Okay? From different sides, but they're both kind of ending right around 1, right? They're starting to look like that. Yes? It won't always be 1. Because why did it end up being 1 in this case? Because the transformation was to move it up 1. In the parent function, the end behavior would approach what number? Look at your parent function graph. What did the ends get closer and closer and closer to but never actually reach for the y values? 0. Okay? So it'll depend on what the transformations are. All right, so I apologize for the PDF messed up the thing, but the information's all there. It's just kind of the charts go on. This should have been on the other page. All right, so horizontal asymptotes are shown on the graph with a dashed horizontal line. Horizontal asymptotes represent the end behavior of the graph. So here's the thing. Let's go back to our graph. We can put on a horizontal asymptote in both of our graphs. In this graph, the horizontal asymptote would be here. And its label would be y equals 1, because that's what line it is. In our parent function, the horizontal asymptote would be here at y equals 0, and the vertical asymptote was at x equals 0. So what did a vertical asymptote represent? They look the same on the graph, but they represent different things. It's really important you know the difference. Yeah. Where the graph is undefined. So can the graph cross that vertical asymptote? No, you plug in that value and it doesn't work. That's why we put the line there, okay? But this horizontal line, did we put it there because it doesn't work? No. We put it there because at the ends of the graph, at both ends of the graph, it evened out to this one thing that's almost like this horizontal line, right? So we put it there and said it'll behave like this at the ends. Did we say anything about what's happening in the middle? No. Can something cross a horizontal asymptote? It actually can. There are things that will even out like this. They'll do all this weird stuff in between, and then they'll even back out like that. The horizontal asymptote there is only there to tell you what the graph is doing at the ends of the graph. Does that make sense? So very different meaning, even though they both are dotted lines on the graph. They mean very different things, and that's important. All right. So reciprocal function, only difference is a 2 here. What is this going to do to your graph? What kind of transformation is this? Stretch, okay? Vertical stretch, right? Because it's not multiplying the x. It's multiplying where the a value would be or the y values afterwards, okay? So this is a vertical stretch. Since there's no shifting or anything like that, okay, that means your asymptotes are going to stay in the same place as your parent function. But things are going to vertically get stretched from the horizontal asymptote. You can't vertically stretch them from a vertical asymptote. You can't measure how far they are vertically. But so in the parent function, you had a point, don't draw this point because it's not going to stay here, at 1, 1. Okay? That point is going to get stretched vertically by a factor of 2. So instead of being 1 unit above the asymptote, it's going to be 2 units above the asymptote. Okay? So it's going to be here. You had a point at 2, 1/2. Okay? It's half a unit above the asymptote in the parent function, but if I stretch it by 2, it's going to be 1 unit above the asymptote. Is the shape of this graph going to look any different from the parent function? It's going to look the same. You'd have to look closely at the points to know there was a stretch there. Okay, so this is going to go like this. And on the other side, you kind of have some symmetry. This one's stretched so that it's 2 units away, and this is 1 unit away. And 2 points is good enough on each side, now that we know the shape. Okay. So if you know your transformations and you know what the reciprocal parent function looks like, these will not be very bad. Okay. This graph has 2 transformations from the parent function. One is the same as what we just did. It still has the vertical stretch of 2. What about the negative? Good. Okay, so it's going to be a vertical reflection. Okay. Again, no shifting here, so asymptotes from the parent function will stay in the same place because we're not moving left or right or up or down. So I already did the stretching. I know that this point ends up 2 above, but where is the reflection going to make this point go? 2 below rather than 2 above, okay? So it's going to be down here. This point's going to be here, and it's going to go like this. So basically, you're taking this graph that you already did right here, and you're vertically reflecting it. So the curve that was above the x-axis is now below, and the curve that was below the x-axis is now above. Last one of this. Kind of written funny, but I wanted you to get the picture. Okay, so if a half is up there, what transformation is happening here from the parent function? Good, a vertical compression. So again, no shifting or translating left or right, so our asymptotes are in the same place. No reflection, so we still expect the curve in quadrant 1 and the curve in quadrant 3. Okay? But rather than the point 1 and then 1 above, it's going to be 1 and it's only going to be a half above. Okay? And the point that was 2 away was usually half above. Now it's only going to be a quarter above. Okay? So again, the curves look the same with all of the stretches and compressions. They just get kind of appear closer or steeper to the asymptotes depending on that. So is everybody okay with the stretching and compressing? So we saw the shifting when we add or subtract something with x, and we add or subtract something after the fraction. And then when you see a different number in here, you'll see the stretching and compressing. Okay? All right, so what is the graph of this? Can we identify the asymptotes, the x and y-intercepts, and the domain in the range? Okay. So before I make the graph, you guys should be able to identify the asymptotes now based on what we've talked about. Okay. So remember, the vertical asymptote and the horizontal asymptote are different. The vertical one is where the graph is undefined. What number are you going to plug in for x here that's going to make this function undefined? -3. Okay, so there's a vertical asymptote at -3. Where is the end behavior of this function going to even out to, or what's the horizontal asymptote going to be? Good, -1 because the whole graph is going to be shifted down 1 from the parent function, okay? So at the line y equals -1, that's where I expect my horizontal asymptote. Now, have there been any stretches or compressions? No. So basically, I can avoid plugging in points if I know the shape of the parent really good. I know that where the asymptotes crossed at the parent, that 1 away from that, there was a point 1 above, right? And 2 away from that, there was a point half a unit above. And then I can draw that curve in. There weren't any stretches or compressions, so it's going to keep that basic shape. And then the reflections of that on that side. 1 away to the left should be 1 below, and 2 away would be half below. So yes, you can plug in points, but it's much faster if you know the basic shape. Okay, so there's the graph. Here's the asymptotes. Okay, x and y-intercepts. To find an x-intercept, what do you do? In any function, if you want to find an x-intercept, what do you need to do? Plug in 0 for y. So if we do that in this case, we get this equation. And I'm trying to solve for x. So the first thing I'm going to do is add 1 to the other side. Okay? Now, this is why we had to know how to solve rational functions or equations and all this. This is like an equation we've been working on in a much smaller form. And remember, we've been multiplying by the least common denominator to cancel x out of the denominator. So that's what I'm going to do here. I'm going to multiply everything by x plus 3. Okay. And that means on this left side, I'm just going to have x plus 3, because 1 times x plus 3 is x plus 3. And on the right side, the x plus 3's will cancel, and I'll just have 1. Okay. I'll subtract 3 over, and I'll have that x is equal to negative 2. Okay. Which means my x-intercept, I found totally algebraically, I didn't even look at my graph, is the point negative 2, comma 0, but that should match with what's on my graph. And it does. Okay, so I know I did a good job algebraically. How do we find a y-intercept? Put in 0 for x. And usually that's a little bit easier because our functions are generally written in the form that y equals with everything on the other side with a calculation with x. So we plug in 0 for x. So this is 1/3 plus 1. So you could either think of that as 4/3 or 1 1/3, okay? Oh, sorry, thank you. Minus 1. I lie. So you should get negative 2/3. All right, so negative 2/3 is supposed to be our y-intercept. I can't tell exactly from my graph, but is negative 2/3 a good choice? Does it seem to match up with my graph? Yeah, so my algebra seems good. Okay. So last thing, domain and range. And we're going to practice our interval notation. Okay. So domain, okay, looking from the left and the right, can you plug in every x value? So is it all real numbers? So if I plug in any x value, I get an answer and a point on the graph. Okay, so you either say all real numbers except for negative 3, you say x cannot equal negative 3. If you do it in interval notation, you basically have to write out intervals that just leave out negative 3. So you would say from negative infinity, so x can be anything from forever small, right, up to negative 3. Am I including negative 3? No. And then that goes with negative 3 to positive infinity. So I know that seems weird, but do you see the way I wrote it? It technically does not include negative 3, right? The number negative 3 is written in each thing, but to include negative 3, what would my notation have to have? A bracket there, okay? All right, so for the range, do we reach every y value, small and large, on this graph? No. Everything except what? Negative 1. So same idea for the range. All right, so this is enough.